Welcome to the session. Greeting of the day. In the previous classes, we have seen about submerged arc welding process. We will see about types of flux used in the SAW process. The same SAW process, the types of flux used. We have know that Garnerer dry flux we are using. But what is the dry flux? What it contains? Already we have seen about the flux coatings available in the shielded metal arc welding. Similarly, it is also contains the alloy system. What are they? We are naming it as a fused flux, bonded flux, agglomerated flux, and mechanically mixed flux of these three. We can, after preparing, we can mechanically mix this any 2 to 3 combination will give the mechanically mixed fluxes. We will see one by one how they are prepared. Number one, I have taken as a fused flux. We have taken some alloy system of raw constitutions, whatever we need for the properties, for the binders, for the iron purposes, arc stability, iron cores, or we have taken mixed, then melted, then quenched. Melted is in the liquid state, then immediately quenching it become nucleated. Point by point it is nucleated, it becomes Garnerer. So that is again it is crushed, nicely fine crushed has been done, then screened with respect to the sizes and graded. So this is the flow, how we are doing. So this is how the fused, the name says fused flux. It is melted and quenched. Melted and quenched. So that word, when it is melted, slow cooling, it becomes complete solid. When it is immediate quenching, the point by point nucleated Garnerers we will get. That we are crushing and using for the as a dry Garnerers in the SAW process. So second method. So we are using the bonded flux. What we are doing, similarly we are taking the raw constitutions, all are in powder. Then in the powder dry format we are mixing, then bonded using sodium and potassium silicate is a binder. So we are using here, and then it is wet mixed. When it is used with sodium and potassium silicate, it is become the bonded using wet mixing. So pelletized, and then later again we are crushing for the finer grains, finer granules. So again it is crushed, and then the size wise we are screened and graded. So this is the path of preparation of the bonded flux. So later, the third one, agglomerated flux, what we are doing here, the agglomerated flux, made similar like the bonded flux, made similar like this same methods, like this same method we have following. But what we are doing, but ceramic binder is used. But the ceramic binder is used, replaces the silicate binder. Earlier what we have used here, some potassium silicates, sodium silicate we are used for bonding purposes. Instead of that, I am using the ceramic binders. So it become agglomerated flux, same crushing. So that screening will be, all process will be same. And then mechanically mixed flux. What happens? Mix any 2 of or 3 of the above. What is the above we have seen? Fused fluxes, bonded fluxes, agglomerated fluxes. Any two or we are taking mechanically mixing from this box and we are mixing. So it become the some desired ratio. This ratio is 2:1, 3:2. Likewise we can able to mix. So what is the positive and negative? Why these fluxes are various types? We will see one by one. So fused flux I have taken. Number one, at the positive point here it gives uniform chemical composition. So uniformly mixed as it is fused. Point by point it is fused, melted and quenched and crushed. So uniformly mixed. But binding, we should do binding operations, mixing, but here it is not like that. So uniform mixing happens. So uniform mixing is good for the mechanical properties. So no effect on removal of fine particles on the flux compositions. Now hygroscopic, this word is very important. Easily handling and storage. This fused fluxes, after drying, it does not have the properties to absorb the moisture from the environment or air. So hygroscopic is a tendency to observe the moisture from the air. So this tendency is not there. And that is why I mentioned non-hygroscopic tendency. If it is not, wetness will not come inside. If wetness is there, hydrogen will come. Hydrogen is there, hydrogen embedded will come there. Therefore, this is a very important point we are using of fused fluxes. Such cases are needed. Easy recycling without much changes in the particle sizes. Very easy to mix and recycle. We have done the process. After the welding process is done, the third and fourth layer of the unfused fluxes, simple warm fluxes, we are recycling back to the hooper, and again we are coming for welding. So this recycling will become very easy. But in case of others, some wetness or maybe this hygroscopic effects will be there due to interaction with the air. So that will not happen here. Easy for recycling. Limitations are few are there. Incorporating deoxidizers and ferromagnetic alloys are needed. Some oxidation will happen, so this is deoxidations to be added in the flux itself. In melting due to need of high temperatures, it also this fused flux also needs to melt at the high temperatures only. So next one, the bonded fluxes. Easy to add deoxidizers. Here it is difficult. See, here it is difficult. Incorporating and ferromagnets needed. It is easy to add deoxidizers, and alloy systems are very easy here. Bonding, one-to-one mixing and bonding allows thicker layer of flux. This is one of the advantages. Limitations, hygroscopic. We are talking about limitations. See, hygroscopic comes here. What is hygroscopic? Tendency to absorb the moisture. Here, this bonded fluxes have the tendency to absorb. Then what happens? When it is exposed to air, it becomes wet. If it is wet, hydrogen embitterment automatically comes into the picture. So this is one of the disadvantages. Drying, warming, heating, bakings are to be done here. Gas evolution tendency. So if it is a hydroscopy is there, hydrogen gas will form. Gas evolution, embitterment. This point are interrelated. Possibility of changing of flux composition due to removal of fine particles. So this changing is getting difficult. So third one, agglomerated flux made similar to bonded flux, but similar ceramic binder is there. So similar property as will be like the bonded flux. It means hygroscopic will be there in the agglomerated fluxes. So mechanical mixed fluxes, last one. The several commercial fluxes can be mixed to suit critical applications to get desired results. What we are doing? We have taken the bonded, we have taken the agglomerated, or we have taken the fuse and mixing. Therefore, two properties we will get. Here some few hygroscopic will be there. There is no hygroscopic. Some efforts will form. Those efforts will be helpful for some critical applications that we are using. Right? So limitations, segregations of various fluxes. What is this? So the segregation is nothing but in the grain boundaries. In the grain boundaries, so let us consider this is the grain boundary. Here, this few alloy systems will form in between the grain layers. The segregation will form during the solidification process. So, the segregation are not permitted to move back or deteriorate the properties, decreases the property, fine grains will not form. If it is segregated in the boundaries, how the next layer will form? Next grains will attach with the previous one and strong bonding will not be there. Therefore, this decreases the property of the material. So during storage or handling, this will occur. And also in feeder recovery systems, where it happens segregation. The segregation may happen during storages, during feeding with respect to attachment to the environments, and also consistency in the flux formation of one by one mixing properties. So you can see the baking of SAW process, how we should do. Some hygroscopic fluxes are required baking process. See, some because of hygroscopic absorbing tendency, it should be removed first. Therefore, it should be baked and remove the moisture. Yes, it can remove the moisture, and such fluxes should be baked as per the manufacturer. How much temperature it should be baked before implementing to the industry? The supplier will give the manual. the supplier manufacturer will give the manual, or otherwise in general they are telling heat up to 300 degrees centigrade for 1 to 2 hours at the oven, and we can take an issue. So that methodology we can follow. So flux compositions, what it contains usually for the alloying system. I am telling this as these various alloying systems can be added for our improvement of the properties. So silicon are there, aluminum oxide are there, titanium oxides are there, iron are there, sodium and potassium silicates are there. So this various property will be included as a binders or improvement of the properties also. Now we are defining one terminology of basicity of flux. What is this basicity? So depending upon the flux constitutions, the basicity of flux is decided. It is a ratio of the content of basic oxides to the acidic oxides. The ratio of basic oxides to the acidic oxides. How much it is there, whether 1:1 or 2:1 or 1:3. Likewise, some ratios are there. Based upon that, we are forming the basicity of flux. Whether it is low, gives some property. Whether it is high, it gives some property. We will see the property in the next slide. So, what are the basicity of flux? Here we have given few of the examples, and acidic constitutions we have given few examples are there. Silicon oxide, titanium oxide, aluminum oxides are comes under acidic constitutions. So this combination makes equal or higher or lower. Depending upon that, the basicity increases or it decreases. So effect, what are the effect? The current carrying capacity, slag detachability. So this basicity decides this current carrying. The flux already I told, when we are adding iron powder, it carries the current along with the bare wire. Likewise, how much current carrying capacity? It having high or it having low. So slag detachability, slag will form, we know this. After forming the slag, it is to be removed. It cannot be used as it is. For removal we need easy detachability, not fixing. It is not fixed, it is not bonded, it is not welded, but it is formed the layer. That layer to be removed. So easy detachability to be there. It is easy or hard. Bead shape. It is neat or smooth or non-smooth. It is easy, hard, bead shape or smooth, or how? That all defines the based upon this basicity of flux based upon this composition ratio. So that is what I have given here. So I have taken two options of low basicity and the high basicity options. What happens? The current carrying capacity, for the current carrying capacity on the low basicity, better current carrying is there. It have the better current carrying capacity. But similarly, there we have low current carrying capacity for high. It means basicity, if it is high, current carrying become low. So that combination you should understand. Similarly, I am talking about slag detachability. Normally we define what is slag detachability. The slag detachability is there. What about the property here? It is in good. It is a good slag detachability. Then the bead shape is good bead shape appearance. And then, but here you see the mechanical properties are reducing. But there we have excellent mechanical property. We have there the excellent mechanical properties are there. So you can tell excellent mechanical property. So what are the other conditions are there here? Moderate slag detachability, poor bead profiles. This opposite are forming there. So here also the poor cracks, but there it is a good crack resistance. Good crack resistance are there. So what we need now? We need good mechanical properties. Excellent mechanical property we need. Poor bead profile, moderate slag detachment. We should consider these factors Finally, we should select whether it should be high basicity index or low basicity. Accordingly, we mix the alloying system, fused, bonded, agglomerated, mechanically fused. So such things we are doing. So welding current. The next factors we should see about in the shielded submerged arc welding process is about the welding current. If it is too high, excessive current we are using, what happens? Low current if we are using, what happens? So if the too much penetrations and resulting into, if the high current is there, high flow of electrons will be there, high heat generation will be there, therefore high penetration will form. More can be welded here. High current, high penetration, therefore more we can go and weld. Full penetration, named as full penetration we can do. But some other points are there. What happens if it is too high? We are not talking about high current. We are talking about too high current. What happens? Burn through are possible. It may come after welding the required thickness. It may comes down. That is totally bad. So burn through will happen. Increased weld shrinkage, much more heat, it shrinks, the distortion will happen. That also one of the possible. Large amount of distortions are possible there. So when I am giving optimum center, instead of optimum I am going with the too high, I am going with the too low. What happened too low? Insufficient penetration. What is this insufficient? Here it is the V group, and here the total length we have to weld. It is the total length we have to weld, and I am welding. This reaches up to this conditions only. It is not melted. Then how it will reach the 0th MO? It is not done. So welding stops here itself. So here is the gap which is not melted. It is the gap which is not melted. So insufficient penetration will happen. And also lack of fusion. This is two words are related. See, penetration and fusion. It is not heated. It is not melted. Then when the two members A and B will join, lack of fusion will be there, and unstable arc. Therefore, current is found unstable. The fluctuations will happen. The fluctuations will happen. It is not joined. Arc is not generated properly. It is not getting the sufficient current. It is not good. You see, I have taken a few examples of increased welding current here. I am from one direction to other direction, I am increasing. How I am doing? I am welding from this direction. Okay. So, when the welding current is, let us consider, welding current is low. Let us consider 100 amps we are giving. Let us consider of 100 amps, number 1. I am giving as a 100 amps. A constant voltage of 24 volt I have given. And when 100 amps given, this is a possibility. It is a low. But required level is 120 amps to be given. When the current is increased to 120 amps, when the current is increased to 120 amps, what happens? The penetration increases. You see, from here to here, the penetration increases. Now, 120 to 140 I am increasing. What happens? Again, depth of penetration increases. Increasing the weld current increases the penetration. That is a point. Current increase, penetration increase. So here we see. Now current I am not increasing. I am increasing the voltage now. What happens? Instead of 24 volt, I have kept 120 amps as constant, and I am varying the. Here I am giving the 22 volt. What happens? It is minimum. The required is 24. Voltage is not given. The pushing is not happen. Pushing of electrons not happen. Then what happens here? It is not reaching the penetration level, but it is reaching somehow to the broader level. So here, when I am giving the 24 volt, this widening happen of the weld bead. Now I am giving the 26 volt. What happens? Even it increases in the weld bead here. So it is small with decreases, with increases with respect to voltage, with increases. But here depth increases. So with respect to increase in the voltage, increase in the bead width, increase in the bead width happens and decrease in the reinforcement. That is okay. Now increasing the weld speed. 3 factors we are seeing here. Instead of this all I have kept and I am going for increasing the weld speed. What happens? So this is 2 are constant. Now we have taken 24 volt proper and 120 amps are proper. And also the heat is generated at one level. But required heat to be absorbed by the weld metal and the electrode. Then only it melts and deposited. What I am doing, I'm moving the gun very fast. Then what happens here? It is not sufficiently heat is not sufficiently absorbed. It is not sufficiently absorbed. Then what happens here? It is not melted. Electrode is not melted, and weld metal is not melted, and therefore we are not getting the jointing increasing, penetration we are not getting, width we are not getting. So therefore insufficient welding speed here. Optimized welding speed to be given, let us consider 10 or 20 mm per second to be welded. But here we have done at 50 mm per second. We are going very fast. This is optimal level we have done. And in case I am going very fast, then 50, I am going very fast. Then what happens? Up to slow we are doing 50, 20, I am doing very slow. 5 mm per second I am moving. Very slow. More heat is generated here and the penetration happens down. Increasing the weld speed decreases the bead width. See, increasing the weld 5, 20, 50. I am going in this way. 5, 20, 50 mm per second. I am speed increasing. Automatically the penetration also decreases. Width also. Here the width is this one. Here it is reduced. Here it is much more reduced. Because heat is not absorbed the sufficient level. We should give optimum speed, optimum voltage, optimum current to be given. For any welding process it is applicable. Current increase, penetration increase, voltage increase, width increase, speed increase, width and penetration decreases. Optimum to be given. This is our understanding. So the welding current 650, 500 and 350. The current is decreasing. Current decreases, we know. The bead also decreases. Penetration also decreases. See, current, high current here it is. When we are going for low current, it is keep on decreasing. You see, it keep on decreasing. The penetration is not happen. Similarly width also. So electrode diameter is there. If you understanding, in case for 1.6 mm, you have to use 150 to 300. It is 100 times multiplied. For example, for just one idea. For 2 mm diameter of electrode. So this is a 2 mm. So this is a 3 mm. This is 6 mm. So the diameter of the electrode I am talking 2. Therefore 100 times 200 into 400. This is an idea. By practice it comes. 600 to 1200 you can able to do. See, the selection of type of welding current. When I am taking the direct current electrode negative, what happens here? The increase in width of the weld appearance happens. But here, when current of direct current electrode positive, increase in the penetration happens. Which one we need? We should decide whether it is to be lengthy or whether it is to be penetrated. These things we should decide. When it is alternating current, both equally occurs. Alternating current. Okay, so that we can able to understand. In the direct current electrode positive, electrode is positive at the top. So electrode melts and deposited with the heat, more heat it comes. So it is penetrated. In direct current electrode negative, negative at the top, positive at the workpiece. Positive melted, workpiece is melted. Okay, that we understand this. Current type, whether it is a positive or negative. Electrode positive, electrode negative. What we are doing here? DC, electrode positive. DC, electrode negative. In such cases, what happens? In the electrode positive, electrons will go upward to the positive and melts the electrode and comes down. Therefore, high heat is generated at the electrode because electrode to be melted. It is a consumer electrode. After melting, it comes down and generates the more penetration, DC, EP. But similar cases, what we are doing here, negative heat is generated at the downward direction. What I am doing, in the heating, I am supplying one separate consumer electrode wire, like TIG welding process. Electrode will supply, heated and melted. So what happens here? Here the penetration is less. Here the penetration is less, but we can able to maintain the non-consumable electrode of maybe tungsten that we can use here. So welding voltages, now only we have seen. If it is too high, what happens? If it is too high, the wider bead occurs, wider bead, this one. If it is too high, wider bead occurs. See, increasing in the voltage, increasing, wider bead occurs. Now only we have seen wider bead. And now wider bead, increasing the flux constitutions, increasing the resistance to the porosity, all will form here. Better gap binding when it is fit up is very poor. Let us consider, I have to fit two components in such a way, but the fit-up is not good. The welder or fitter is not done properly and is done fitting with a wide gap. At this time what I can do, at this time I can able to do a large diameter. A large diameter electrode I can use, instead of 2 mm diameter I can able to use 4 mm diameter, and then I can able to fill this gap. Some better gap bridging. The bridging terminology for this gap bridging, when the fit-up is very poor, at some time it will be helpful. So low voltage will lead to resistance in the airflow. Similarly, peak narrow beads and poor slag removal, this all are not good. We should be modified. So welding travel speed, what we have discussed is the same points. It is too high. When the heat is too high, low net heat input at the per point, per unit length. Heat is not generated at a specific point. Here we have to weld. This location heat to be absorbed. This location heat to be absorbed. This location heat to be absorbed. When I am going very fast travel, what happens? Heat is not absorbed at this one point. Similarly, heat is not absorbed at this point, and heat is not absorbed at this point. Low heat is input per unit length. So less material to be deposited. Heat is not made, then when it will be melted. So less material deposited, all are interrelated. See, these are interrelated. Less welding reinforcement, obviously less reinforcement will be there. Shallow penetrations, deeper penetration will not happen. Increase the tendency of undercuts, increase the porosity. This all will happen when this travel speed is high. Uneven bead shapes. First of all, it should be heated. It is ready to melt, ready to deposit. That we are not permitting. If you are not permitting to heat, this all weld reinforcement will be less penetration, less material melting, all will happen. To low welding speed, reduced porosity, reduced slag inclusions, and increased melt through will be possible. We should give time. Optimized we need. Optimized speed. We need this one. So electrode sizes, we see I have taken a 500 amp, here also 500 amp, here also 500 amp. But I have taken the variation of 2.5 mm, 4 mm and 5 mm. Increasing the thickness happen, but the current is same. In such case, what happens? The same current supplied for a small diameter, the proper welding occurs. Proper penetration is formed. But now the same current is applied for the increased thickness. It is not sufficient to melt the required diameter. Therefore, what happens here? The length of penetration decreases. And now further I am increasing, for example, 4 to 5 mm. The diameter further increased, but the current is given same. It is not possible to melt as per the given current. What happens? Again it is decreased. From here it is like this penetration, and the second condition it is reduced, and third condition it is further reduced. I have used 2 mm, 4 mm and 5 mm electrode, all for 500 amp of current. So optimized current to be given. So optimized current. For 2.5, 500 is okay. Diameter increase here also 600 amp to be increased. 5 mm here also 700 amp to be increased. Okay. So therefore material transfer in assembly, how it happens? So you see here welding current is there. Current is increasing in this direction with respect to 3 mm, 4 mm, 5 mm. So the same point what I told here, it is reflecting in the graph format. See, for the 3 mm electrode, you can able to go mean number of transfers. This means I am talking about this transfers. How much drop it is melted and deposited. It is about 50 drops are there. See, about 50 drops are there. But similarly, when it is increasing, the same point reaches, when it reaches the same point for the 600 current of amp for the 400 mm, it reaches here. In case 500 mm, when it reaches 800 mm only, it reaches this point. So increasing current, diameter increasing, it should be neatly, we have to check this. Obviously optimized current and filler wires to be matched. See, here I have taken the 3 mm electrodes, here I have taken the 4 mm electrode, here I have taken the 5.6 mm electrode. What happens when thickness of the electrodes are increasing but with respect to same current, same voltage? What happens, you see, the deposit at the same current and the same electrodes, a higher current density, a higher deposition rates. Here it is increasing, but here it is keep on decreasing in this way. You see, it is keep on decreasing as compared to the first one. So this is what the falling of the wires. So we may use at the submerged arc welding a single filler wire of welding of this method, or otherwise we can use the double fillers if the thickness is more wider. For small thickness we can use a single. For the large thickness we can use the double filling methods. Such things we can do in the submerged arc welding processes. So some other electrode extensions, where the electrode extensions increases, obviously the penetrations also decreases. The summary: in welding, we have seen today about the submerged arc welding process. In that we have seen about the electrode, the fluxes, and then the current, voltage, welding speed, factors, how it related with the welding processes. The remaining part of the subjects we will see you in the next session. Thank you.